world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate.
Welcome, lads and ladettes, to Aether Roundtable number 111, Gravimetry. Take it away, Shane G.
Wow, you've got the correct pronunciation and everything. I love it. Thank you, Kat. So yes, as we see here, I took the time to put the pronunciation of the topic on the cover slide, so we don't have any mispronunciations. Gravimetry, or the study of Earth's gravitational field, so-called, as we're going to go over. All right, so that's how it's defined, the measurement of gravity, typically depicted as the geoid, lumpy geoid over here. And in the background here, we have a very common image. They actually have this as arrows going from the globe to the ellipsoid and the geoid model. But as we're going to go over today, it actually works quite the opposite. The ellipsoid and the geoid come together to create that which is the globe. So gravimetry simply is the measure of local downward acceleration. That's really what it is. Put scientifically, they say to measure the acceleration due to gravity and the local vertical component of it. It's also used to detect lateral density variations, as PhD Tony would tell us. They use it for scientific, I don't know, whatever he does besides flat Earth seismology is his expertise lapsed over a little bit. So they actually use gravimetry and gravimeters to detect things and use density. Not saying that that's detecting the field of gravity put out by mass attracting mass, but it is detecting, say, variations in the local downward acceleration. What we're going to look at is a bunch of anomalies in the field maps and structures, and it's going to be a lot of numbers without ledgers, and it's all going to be in milligals, which are very tiny amounts of variation that we're going to go over. So from Wikipedia, we have our gravimeter, of course, is just an instrument used to measure the gravitational acceleration or the local acceleration downward. They usually use spring balances, which is the most common and the basic one, to measure differences in the downward acceleration by weighing a mass at different locations. There's different variations on that method, though they all do the same thing in principle. We're going to go through a couple of the different ways they do so just for fun, so that we can say we all went through our introductory to gravimeter course before we started using it to talk about gravimetry. So again, all this is ever doing is measuring the rate at which something falls downward. So basic principle, of course, measuring the local G. The types of gravimeters we're going to go over, or gravimeters, would be spring, absolute, superconducting. I think there's an atom one as well. It's important to note here that they say that the gravitational field is latitude dependent, which would mean it would be stronger at the poles than at the equator, right? Because of the spin and the centrifugal forces from a spherical Earth, obviously the force known as gravity would have this latitude dependence. However, when they measure it, and when they model it, and when they depict it, and when they show it, and when they talk about it, and when you plot data, they ignore all that, and they only plot the difference between their perfect ellipsoid and what they measure. So then they get this lightly varied geoid ball here. This is, as you notice, not showing the gradient color dependent of a latitude dependent force that you would expect. If this is measuring the local gravity field and gravity is latitude dependent, then why don't I see a color gradient extending from the poles to the equator? Because they ignore that completely and they only do variations from this model over here. Something very important.
Shane, real quick, this is Shalom. The volume on your YouTube channel is non-existent, just about super low. Alan's is fine, but your channel's kind of jacked.
My chin. Okay, hold on.
Yep.
That should be better, I think.
Now that's a lot louder.
Yeah.
Yeah.
There we go. Switched it over. Cool. OBS switched to the other mic. Thank you, sir. Should I put it down here? No, we're good. So about latitude dependence on this gravitational field. When they go to measure it, they always know that it is latitude dependent, but what they're actually talking about is a variance somewhere between 9.83 meters per second squared to 9.78 meters per second squared, which is tiny. And that's not what this is showing, by the way. This is showing a tiny variation that we'll go over in a second. So again, latitude dependent corrections in gravimetry are actually not ever measured. They're introduced via the model. So they're always introduced via the model. They're never actually there. So they're not a product of them. Again, they have the expected model that we went over before based on the centrifugal force and the stronger at the poles, weaker at the equator. And that's what they're assuming. And then they quickly ignore and dismiss any correlations so that they can measure the actual field. Something to consider as we move forward. So gravimeters are essentially accelerometers. The first ones were. They're just measuring the downward acceleration, and they have a tiny threshold from which to do so. We're going to go through a couple different options through the ECGS, or the European Center for Geodynamics and Seismology, which I'm sure is actually just some dude's basement over there. So again, there's a scientific rigor and the need for finding the variation in local G, as they put it, is of course the determination of the geoid model, which for them represents the mean sea level of oceans, and which they do extrapolate, as we'll go into. It's also pivotal in wrapping mean level sea level around a globe or an ellipsoid model. They say for tectonics and post-glacial rebound, that's to do with global warming and nonsense, influence of atmosphere and hydrosphere, right? So that comparing the measurement variation of local G to atmosphere. And then, of course, the structure of Earth's interior. They're making great leaps and bounds to guess at density variations based on their supposed mass-attracting mass, which they're also assuming and presupposing relates to this local measurement of G. Now, we're going to go into a little bit of kinematics and dynamics, but as far as gravity is concerned, kinematics and the measure of the motion is just little g, the measurable downward rate at which things fall all over the Earth, around 9.8 meters per second. And then big G would be the cause for that local downward acceleration, or the dynamic cause in physics, meaning the thing that does the moving, the Y. And of course, they assert that's mass attracting mass, but those two things are decidedly separate. And what we're going to be dealing with today is entirely only local G, small g, measurable acceleration, nothing to do with the cause of anything. Gravimeters actually don't have anything to do with the cause. They only ever measure the local variation in G. That's just says here. So again, we're going to go over the absolute and relative gravimeters. So an absolute gravimeter means that it's allowed to free fall inside a vacuum, and then its position is measured, usually with laser interferometry and time within an atomic clock. So think about how sophisticatedly accurate that would be. They drop a test mass in a vacuum, and then they beam it with interferometric light to time it, and then they measure the wavelength to get exactly the rate at which things fall and the variance therein. So that's what that's doing. That's what that would look like. This right here is probably, I don't know, the Rolls Royce of the best gravimeter you could ever get your hands on. It's a 3 gradimeter atom interferometer. So it's got 3 chambers in which it's doing this: an upper gravimeter, a central gravimeter, and a lower gravimeter, and is doing this in 3 dimensions, and also measuring it against itself to get this wonderful profile here. So this one right here is 3 vertically separated atom interferometers in the same tube, with the source masses are these gray cylinders around the middle section, and it slightly modifies the gravity field in that region. So this is also they're saying that these are affecting the gravity field because they're concentrating masses over here, and thus the field would vary over here. So that's super neat. What they're doing with that tool is launching cold atoms at each gravimeter, right? A cloud of atoms is cooled and then launched upward, and then they use interferometry to split and mirror, and then they get actual recombinant phase patterns from the atoms. So they're not doing laser interferometry, they're doing from matter waves, or so they claim, recombining for the matter waves. So they're bouncing interferometric beams off of atoms and then measuring that. to get the
So-
local variation of G.
For the lay crowd, they are sciencing the shit out of it.
Yeah, like really. I'm pointing this out because the lads know how specific and crazy this is, right? Using laser interferometry to measure it, to actually bounce off particles in a vacuum tube. Like, all right, we know that things fall at a rate, and I believe that you're measuring that rate. And so again, spring gravinators are the most common. A mass hangs from a zero length spring, and they do something of a gravity change as it elongates delta G over here, and they do the same thing. There's also superconducting gravimeters, which we'll go over a little bit, and then the atom interferometer ones, which is the one we just went over. That's probably the most complex, most scientifically attuned you could possibly get. And again, back to our boys at the ECGS, the European Center for Geodynamics and Seismology. And we're going to look at this, what an absolute gravimeter looks like. It's installed in the, whatever this is, Wolferdang's underground laboratory. It truly looks like someone's basement, but I assume this is a high-tech research lab for all of Europe, as the name implies. But here's the beast right over here. And then here's our lads and ladettes working on it with all their fancy equipment.
Now she is sciencing the heck out of it.
Right?
Those other people were just kind of messing around. This is where the science begins, right here in the basement.
Well, honestly, the level of science is determined by how much blue light you have. And as you can see here, this eerie illumination means that she is indeed sciencing the shit out of this. And then the only other one is this superconducting gravimeter, which again is in the same place, the Wolferdang Underground Laboratory. And it does its thing to measure consistent supercurrents, I guess, which are trapped in superconducting magnets to produce an ultra-stable magnetic field, which levitates the superconducting test mass. And then that's measured by persistent currents and niobium coils. And I'm not going to pretend to understand what any of that means. But they do the same thing with a high degree of specificity. And here's what that beast looks like in the bottom of their basement lab, and I assume a scientific laboratory. Now, all that is really context for what we're going to go over and how we're going to analyze it, because when it comes down to it, again, well, how much are we talking about? All these instruments and all this precision is great, but what are we really measuring? If it's 9.8 over here, it only varies, say, by 0.3 to 0.4% totally. Now, to put it in the milligauss scale, when you're looking at the geoid model over here, again, this is showing a colorized gradient of gravitational anomalies in milligauss, and again, anomaly defined by variation from the static mean of the ellipsoid model that they put forth, not the actual anomalies and variation by latitude or measurement or anything. And it ranges from -50 to +50 milligauss. So converting that over here, you get the actual variance of what this is showing with this wonderfully neat red and blue and vibrant colors, a variation of 0.005%, or roughly plus or minus 0.0005 meters per second squared, just to put it in perspective. And of course, here's that wonderful diagram that we're going to see a bunch more through this over here, and it's through the geoid model again, and this is the measurement of the variation of local downward G, and it's measured in milligauss, and again 50 and 50, this is what we're looking at. So this deep red is actually almost identical to this blue in reality, but because of the scale, it looks mighty different and these giant peaks and valleys.
Yeah, can you back up one slide just for a sec? So the milligal, or the gal itself, is not a measurement of force, of gravitational force. It is the observed acceleration. So the gal being 1/100th of a meter per second in terms of acceleration, milligal being 1/100,000th of a meter per second in acceleration. This isn't a force they're talking about. This is the effect that they're measuring with this unit. And that's really crucial.
Yeah, very excellent distinction. Thank you, sir. Very, very, very good. Yep. Absolutely. And again, I couldn't have put it better, and I probably wasn't pointing that out clearly. That is a very good distinction to make. Yes. Now, we're going to go over a couple of the models here, but again, this is the geoid model, and we know about our ellipsoid model, but we're going to show how the geoid is actually derived from the ellipsoid, not the other way around. This is actually from a paper that I saw our boy on Twitter put out over here. I think his name is First Run. He put out a custom proton link that I went through, and some of the stuff he put forth was excellent. And I'm going to put this one here because this goes over how the geoid is derived from the ellipsoid. It is part of his surveying and geodetic and land surveying output, but everyone should go check him out on Twitter. I'll link him in the description for everyone. But this one goes over how the geoid is specifically derived from the ellipsoid, even though it's been adopted as the reference surface. So you need to have height variations, and how you, if the basic premise is if you're measuring 9.8 meters per second squared down, it's above the surface of what? The height above what? How high above what? The surface of what? Then instead of being the actual Earth, it's always the surface of the ellipsoid, which is how you determine heights, which is how you have to tie it specifically to the ellipsoid model. So it's actually defined, right? It's chosen as the computational reference, and then you get the data to wrap around the model, not the other way around, as some may suggest. And again, the modern geoid is built on top of your chosen reference ellipsoid. You always have the WGS84 first, whatever model you want to use, because you need your semi-major axis and flattening ratios and metrics to be able to fit the geoid model over that and to have any variation from it. And again, as I tried to say in the beginning, it is computed only as the irregular equipotential surface showing where real gravity and topography deviate from that smooth ellipsoid. Now, this is so unnecessarily complicated. Again, we're not measuring just the variation in G as you would think. It's no. We're going to assume that it's constant everywhere. We're going to ignore latitude dependency. We're going to make a constant ellipsoid model, and then we're going to show you how much it deviates from that hypothetical. Okay.
All this bit here is really them they're just messing with R squared and presuming the radius of 3,959 miles. Check the variance in the ellipsoid. A couple hundred feet?
Yeah.
And what percentage that is of the radius? These are the ninth decimal place calculations that they're pretending to make that are almost, at a lay person level, totally unfalsifiable. This is all trust me, bro.
Yep, and none of it exists without this ellipsoid model as the framework, as I'm trying to point out. Like this has no meaning outside of this framework. The two are related. You need the ellipsoid, it says here, defined first. Always, forever, has to be, right? So all geoid models, and here are some of the actual numeric designations, DGM 2008, geoid 18, whatever, are explicitly referenced to a reference specific ellipsoid. If you change the ellipsoid model, as Stone point out, all the heights are then relatively changed because they're always defined relative to geoid and the ellipsoid. So again, that's where it's crucial. That's where it comes from. So we know how surveying specifically also ties to the ellipsoid model. And we know that if you were to measure the surface of anywhere up to 100 miles, it would measure measurably flat, and they consider it practically flat for all purposes, for surveying, building, construction, etc. Only into 100 square miles, I think, or 225 square kilometers, I forget. Up to that point, do they need to treat it or incorporate so-called curvature, which means they reference back to the ellipsoid model. So again, they need the ellipsoid model to have curvature, to have anything that resembles curvature. It's tied to everything. Now, how they claim to use both of those models and gravimetry and satellites and the GNSS network to prove the shape of the ellipsoid and geoid model is through this neat picture over here. Pulled this off Google. This looks like a nice classroom demonstration of what they're trying to go on here. So they're saying that the accelerometer on the aircraft measures the specific force acting on the instrument. And then they're saying that the GNS system over here, which has the multiple satellites and the stations constantly connecting to it, gives the kinematic acceleration of the aircraft's center of mass along its trajectory at about 9.8 meters per second squared or whatever. And then they subtract the acceleration from the accelerometer specific force, which then yields the local gravity vector, which they call g of x prime over here, at the aircraft position. And then difference from a reference field give a new one on the order of magnitude of 10 to the negative 5 meters per second squared. So crazy that this is what they say is happening, and all of gravimetry to produce this gravity field, which looks super impressive and precise and scientific, but all they're doing is using their network of embedded, internally consistent ellipsoid model references of WGS84 and other ellipsoid references within all three of these independent systems. The planes use it, the satellites use it, definitely uses ECF. Everything is linked to WGS84, and then the ground stations, of course, being linked to WGS84, and they're all working together to so-called measure this parameter of this deviation within this internally consistent model that they put forth. So again, this is just a description of what it's supposed to do. It's doing regional modeling using all the components of the supposed variation of a local downward G. Now, what we're seeing, actually, it should be important to point out that it explicitly presupposes that model. So it's not a sphere because that's the measurement and that's what the measurement shows. It's a sphere because we take our measurements and we always put them into our ellipsoid model. We reference it with latitude and longitude. We need an ellipsoidal height to get our geodetic coordinates in the first place, right? You need a spherical reference ellipsoid or none of this works. So that's why it looks like it's a sphere. Counter to what you would think that, hey, let the data define the shape. And if that data is a sphere, that'll be the shape that it'll assume. No, my friend. Pre-assume the sphere, then make all data fit that sphere, and that's how we do it. That's how it works. That's how you get your ellipsoid, geoid, geodetic height. And again, it seems unnecessary, but the way that the magic happens, the way that they hide the model, the way that curvature and adherence to ellipsoid model gets hidden is through this height transformation. They do a specific equation for heights via the ellipsoid and the geoid and orthometric. And they use the translation between all these three to produce a graph of negative heights, which is then wrapped around the ellipsoid model to literally curve sea level to make it curved, right? So when they say, haha, level is curved, it's because they're literally taking level measurements using intermediary layers of ellipsoid and geoid heights to offset the difference, and then wrapping those sea level measurements around an actual sphere so that, yeah, they've made it definitionally curved. Kind of crazy. And again, here's just a really bad quality illustration of that. Your orthometric height, your ellipsoid height, and your geoid undulation all taken into account to actually hide surface level and wrap it around a sphere. The equation they do that is H equals big H plus N, which literally and mathematically wraps flat mean sea level references around Earth's ellipsoidal shape. And they use it, they say, we have to account for gravitational irregularities, which is why we have to wrap it around our pre-assumed sphere. But again, they've assumed the sphere to wrap their gravitational irregularities around when they were taking the model measurements in the first place. So it's all very circular. Well, any questions so far? I feel like take a breath.
No, you're doing great.
I think
So, Stone,
Awesome.
quick question for you: how this orthometric transformation relates to, and the gravity potential relates to your ILS measurements? So, like, essentially, they're saying that there's like a 300-meter gravitational offset that's making the water, deviate like negative 300 from being level out in the ocean to make their measurements work. Would that kind of be like,
that is cool. That is quite the feat, isn't it?
dude? Oh man, unlucky. And then that didn't, and then that measurement didn't even happen for them. So they were off of their orthometric predict. Like, we could reference that location, see the gravitational deviation there, and then like show how much this hypothetical model is even off. You referencing Stone's thing, right? It would go in tandem with that.
Yeah, and I mean, it's like, so just to put it in perspective, this is the only line that's real, right? This is the ground. This is a real tree. This is a house on a hill. This line is made up in a fabricated ellipsoid model, or a fabricated geoid model. Doesn't exist. It exists somewhere below the actual surface of the ground, can never be measured, verified, etc. Below that, somewhere, hypothetically, is another not real line model that doesn't exist within the ground, somewhere that can't be measured or identified, that's going to be different from the first two. That's what they're saying. And then they're like, okay, look, we need to do all that. And then they use this formula, ellipsoid height, geoid undulation, and the actual orthometric height to relate heights through this, which then, again, has the effect of taking what would be level and mean sea level and wrapping it around this shape right here. So
Awesome.
that's important.
The one thing I would tack on to the end of my first thought about milligals is how It is intentionally, again, just like they did with the apparent magnitude star scale. You know what I mean? The whole thing where it's logarithmic, it's 2.5 times to the left, etc. Here we're talking about a quote milligal, where in the rest of the metric system, for example, milli means 1,000th, but here it means 100,000th, and that's where they're snowing you by a factor of 100 just by the terminology being used. Isn't that fun?
Crazy. Stone,
I
you're
would say
echoing a
it's
little bit in the background too, or something.
Oh no, that's my wife on another call.
Gotcha.
Hey, this colorful picture of the Earth, it looks like it has a really bad rash.
I would say it looks infected, but whatever. Like,
Yeah, some kind of fungal infection coming out here, breaking the skin. Totally.
yeah, they're using one factor of 100 to show you how much it doesn't matter and how little it deviates, but they're putting it in vibrant colors and they're making it very impressive. Now, if we remember from our previous presentations, we always know that the globe, as we said, is a product of the terrestrial and celestial sphere models. And we know that, in fact, when you overlay, say, right ascension and declination from the celestial into latitude, longitude from the terrestrial, you get a difference. And then that difference they call the astrogeodetic deflection, also known as deflection of the vertical. And it's when those two coordinates don't line up. There's a difference in the variance. It's through astronomical latitude and geodetic latitude. And again, when you put these together, this point matches this point precisely, except for a little bit. And that little bit is what this is talking about. And again, we're not going to go into this a lot, but again, it's astrogeodetic deflection, as geodetic deflection, subset of geodesy, meaning that the study of Earth and the study of the stars are inseparable. And then this is just in layman's terms, this is a deflection of the vertical, DOV, but literally it's only a reflection of the combination or amalgamation of the celestial and terrestrial on a point-by-point basis. Right, so they transform the coordinates, and again, they use the gravity vector, but mostly we're talking about, we know how they do that for that model, and now we know how they do that for the geoid model. The geoid model gets introduced as well, and this is actually a meme that you'll see how they explain it, right? And as we started with in the beginning, they were like, listen, our wonderful Earth is so cool, it creates these two models that we need to map it. Like, we can't map this. No, we need to use these two for sure. And these two are a product of this. So they're saying that, because the Earth is spherical, we need to have both the ellipsoid and the geoid models. And again, usually represented by our lumpy geoid over here. But as we saw in the geodetic datum presentation that I did, that actually those two things don't equal the globe Earth. Those two things equal a datum. They're still models, right? So together they have their gravity field, their celestial terrestrial navigation, and they have reference and what we call east and west angular separation and north and south angular separation, or latitude and longitude, on this new created graticule.
So they got together to produce an idiot child.
The lumpy sphere measured the other sphere, and they came out with the lumpy measured sphere. Yeah. So, and again, I think that it's much more accurate to put them like this, right? So because we create this model, and then we create this model, as we found out, that has to be the order of operations. You cannot create this and then this. You cannot create this independent of this. So the order of operations then must be this, and only then do you get this. So infrastructure of the ellipsoid model, which is our spherical, assumption. And into that assumption, we shove our tiny variations of G and presuppose cause of the downward acceleration, getting our combined datum. And then from that datum, everyone presupposes it's the Earth. And then from these combined abstract 3D coordinate systems, we have people unable to distinguish this from a theoretical or a concrete globe Earth. This is the amalgamation of two spherical models. This is what people confuse this for.
The old switching bait.
We'll correct the vertical and adjust as we please.
As they say. Exactly that. So now moving into a quick kinematics dynamics brush up, as we say. So gravimeters do not by themselves do anything to do readings causing gravity, of nothing of the sort. All of that is through and inflicted through what we call an interpretive framework of people who subscribe to Newtonian relativistic dynamic gravity, etc. Nothing that we've talked about, none of the instruments, none of the gravimeters, none of the measurements have anything to do with the cause of gravity. It hasn't been touched yet at all. But if we were to delve, right, again, kinematics and dynamics, kinematics is us saying that with the rate at which things can fall, and we'll go over this in just a second, and then dynamics being why they fall, right, the force behind it, the supposed force behind it. But again, we have nothing to do with the cause of gravity here, and if we were to speculate what the cause is, the way that they interpret the local varying measurements of G through this dynamic cause of big G is they say, look, every mass exerts a force on every other mass, and because of that, we have little g, and therefore when you measure little g, it's because of big G. Honestly, that's the way the logic train goes. Now, is the cause of what we're measuring on the geoid then, is the cause of this local variation in G, is this the measurement and the map of the variation of mass attracting mass via a density of Earth's surface? Or is this a density gradient of the curvature of space-time induced by curved linear geodesic paths of constant acceleration that actually is causing mass attracting mass effects? Or is it none of those things, then it's just a local variation of G? If someone's going to tell me that what we're looking at in the geoid is a map of bending and the warping of space-time, as that would be the dynamic cause of gravity currently subtended, then I would think that that's pretty funny. Obviously, that's nothing of the sort.
Can you go back 2 slides just for a sec? To the geoid pic. That one, yeah. There it is. Did you notice that the big red splotchy thing and the big blue splotchy thing are both over the ocean?
Yeah.
Hmm.
Oh, yeah. We're gonna go into that in quite a bit, actually. I think we have some maps that we're gonna look at and see exactly where that plays out, how it varies.
Yeah, what's with all the
etc., and
undulation going
what
on
that
there?
means. Yeah, look at all the geoid undulation of the local gravitational field that happened just over, this is by month. So it's constantly changing, as they say.
That is staggering.
Wait. Don't they say the discrepancy between the two is due to like basically the density of the ground going all the way to the core at that location? How could it be varying month to month?
Yeah, isn't that crazy? You know what would be varying, though, if we had a different dynamic cause of gravity that was influenced by, say, electromagnetic toroidal fields that had some sort of migratory path that had to do with the sun and the moon? I mean, it might look a lot like this.
Oh, now that's just crazy talk, buddy.
Right? This is from Wikipedia. It's the global gravity anomaly over land by year.
So is it just cyclical then? Just every year, every month, it just fluctuates like that, back and forth, or what?
Well, again,
Or
this
is it
particular
kind of
map
random?
this one is 20, negative 20, and positive 20. So it's less than half of our other variant, which was already microscopic on the 100th of a degree, right? So what does this mean? Who the fuck? Like honestly,
Yeah.
as I started with
to quantify, that's 20 or minus 20, 100,000ths of a meter per second change. 20 to minus 20, 100,000ths of a meter per second.
Yeah. Yep. Yeah. So again, what does that mean? I mean, I don't know. They have we've seen a lot of models before. We had a tide chart. We did all the other models. It looks like everything around the Earth is dynamic and it changes all the time, just like the electromagnetic flux, just like electromagnetic fields, just like the actual everything that they measure that has to do with the Earth is always constantly in motion, right? The dynamic force of the sun and the moon usually cause everything, I think. So a quick picture of, is it mass attracting mass causing our gravimeters to fluctuate, or is it's bending and warping of space-time and how the two relate? Of course, the general relativity reduces Newtonian gravity to the curvature that can be encoded, et cetera, as we went over before, right? Because it's the curving and curved space-time, which then induces the curved geometry of the following the local geodetic, which is how the gravitational forces are created. And that's supposedly what people think they're measuring when they have their gravimeter measuring the local variation on little g. However, does little g depend on big G in the practical sense as you measure it? No. No, it does not. It can be totally separated from it, meaning it's just a measurement or a kinematic description of the rate at which things fall. And again, it can vary at different places, as we saw with our maps, as we're going to see later. But does that mean anything to do with the cause of the reason why things fall? No. No, which is why we can reduce it to this 2h over t squared, which is, as we'll see in a second, the kinematic equivalence of how to just get what little a would be, meaning all you need is how high something fell and the time it took to fall to get the rate at which it fell using basic physics, right? You can start off with h equals 1/2 a t squared plus vt, right? And we have the height above the ground, the rate at which it's going to fall, the time it takes to fall, and the initial velocity, which for our simplified from rest example is 0. So then do some algebraic shuffling and you get little a, which is what you're going to solve for, equals 2 times the height over the time it takes to fall squared. So does this depend on this? No, absolutely not. No, this can be measured independently all over the Earth, as we're showing with our gravimeters, absolute and relative, superconducting, atom, etc. We're showing that this is indeed measurable and varies. And it has they're gonna have to do a lot more work to connect this to big G and how the dynamic, bending and warping of space-time or mass attracting mass is actually causing and related to this. So again, to put it real simply, the local acceleration, or what we're measuring with gravimetry at all, is this change in A. They call it little g, and g of x in their functions and their diagrams, but could easily be little a, and it breaks down to an equivalence of 2h over t squared. So therefore, does not directly depend on the gravitational constant, but gives you a way to calculate from just the distance it fell and the time it took to fall. So if you want to calculate it without g, you would do this. You would do this exactly. You do just this little a. Now, to put it in a real world example, you can say, hey, if you drop something from 10 meters and it takes 1.43 seconds to fall, you just fill in your variables here, 2 times 10 over 1.43 squared, and then you got 20 over 2.0449, comes out to 9.78 meters per second, which is just utilizing this in a real world equation. So the way that the logic train would work is, because they know that these are related, all you do is when you measure this, you just throw it in and substitute it. Just throw that in this equation and boom, we got it.
If you check the main chat real quick, I have a slide you can add to your Prezi right now if you can pull it up in there.
I think they should
Main chat.
rename their astrophysics as algebraic shuffling. I like that term.
Yep.
Little shuffle.
I like it a lot. That's really all it is too. Yeah, I do like that one. It's always been that way. Yes. Yep. We'll add that for later. So to get at the dynamic cause, as we were saying, they have to say, hey, actually, we need a whole bunch of other variables and constants. And they say, well, actually, because we know it works in celestial calculation, supposedly, and that we know what causes tides, again, an assumption and not correct, then thus we know that it's actually the force. So that we know that it correlates independently with our perceived distributions, and they do their calculations based on density to get the forces based on the masses over the radius squared, of course, which is this right here. Now, this actually doesn't prove anything at all. These are dynamic tests. They're saying change all these around, watch the gravimeter, and then see if it's equivalent with changing this. This is a proposition to see if it is correlated, not proof that it is. In fact, it's not correlated at all. So when we're doing our algebraic shuffle, as Liliana likes to call it, is it legal? Can we do this? Can you just substitute little a for little g in the Glober's equations and be done with it? Of course you can. They won't like it, but you absolutely can. It's just the local acceleration downward due to whatever. Replace this with big G and call it whatever you want. It's a variable now, unrelated to this. As we'll go through, You can, then they say, look, well, you can't have buoyancy without gravity, you dummy. Duh. Would you know the formula for buoyancy? It's got G in it. Boing, right? So actually, you can redefine it with A. Look, now my formula for buoyancy doesn't have G, it just has little a, which again, if you're reminder, can be solved for on the fly using height and time. So solve that little equation. Boom, we got our buoyancy formula. And we can do the same thing for mass. You can't have mass without gravity, guys. Wrong. You can have little a being 2h over t squared. Now we have a new formula for mass. Easy. Same thing with weight, etc. Say you can go through all of the actual formulas that they say are dependent on gravity are just dependent on our solved little a. Right. So now again, we're going to look at some of the maps on how they have projected this and their supposed greater meaning of what they say this means, right? So first of all, their model relies on interpolation, meaning some points are unknown and they solve based on the average or mean of other known points, which is required if you have a model. You can't do any of that unless you have known positions to adhere to in the first place, which of course is the ellipsoidal framework that this is held within. And again, you need latitude and longitude, and you can't have any reference within here without latitude and longitude, which is, of course, the ellipsoid model. Now, it's important to point out, because I think our boy Dom had a enthusiastic gravimeter lad who wanted to say that he knows that his direct measurements could independently prove the shape of the Earth, and that's just patently false. Actually, you can't actually. All of this is wrapped around the ellipsoid model. These are not independent measurements. All you're measuring is the local gravity field. You're not measuring anything to do with shape. Curvature is induced from mathematical modeling and your interpretive chosen framework. So again, we're going to go through our gravity map anomaly with our variation over here. It changes all the time. They know that it varies with latitude, but again, that is not what we're measuring here. This is a tiny, tiny, tiny variation. Why they won't model this, I think this would be much more interesting. None of the maps I have model that. No. So here's our basic gravity anomaly in our milligals as we started out with. So now we have our gravimeters. We've gone all around the world. We've taken our measurements, and there is the result. So when they say, hey, we know that gravity's real because we have this map. Can someone make a statement about what they think this map shows them about anything? Anyone?
Especially with respect to latitude. Wow.
Anything. Wide open. Show me something important that this map tells you. Yeah, because I couldn't think of one, but this is what they have banded around everywhere. And again, the result of the specific and highly precise interferometric light bounces off tiny vacuum suspended atoms to the degree of specificity to get 60 plus or minus 60 milligals. That's what this represents. And then how does that look on an orthographic globe? Well, like this, right? All these hot spots looking super mean. Again, tiny between the reddest red and the bluest blue is 120 milligals. So almost nothing. And if we were to say, oh, do the blasphemous and project it on azimuthal equidistant, it's the same now. Does this say something different than this, do you guys think? Is this saying the same thing as this? What about if we put it on an azimuthal equal area, which is slightly different than our azimuthal equidistant projection? Or we could even do our concave and dual pole lads and put it on a dual pole map, which is, of course, the azimuthal equal area centered on 90 north with the same projected coordinate system and your prime meridian through wherever you want to put it. But again, what does this tell us about anything? To me, nothing significant, but this is what they put forth. Now, if you notice, this has the same data, right? There's this big blue bot across the coast of Africa, big blue bot over here. This map, again, is in a little bit different. It's up to 100 and down to 80. And if we take that same map and put it on the orthographic globe, we have this, measured in milligals again, or of course, measured in azimuthal equidistant, back to our equal area, over to our dual pole lads. And so this is what it's showing us. Super informative, maybe. And here we have the same thing measured a little bit higher up. So if this is at surface level, this is what they're saying. It's, you know, it measures a little bit higher up. I'm not sure how high up, but it's the free air gravity anomaly from the EGM 2008. And it's in up to 80 plus or minus 80 milligauss. Here's what that looks like on the globe. So here's what the actual data looks like in our chosen input format, equirectangular. Of course, this is cylindrical because you have the poles being super distorted and the distortion in here, but this area is minimal. And you have the orthographic load projection over here. It seems to align with continents. And again, back to our azimuthal equal area, or equidistant, sorry, and then over to our dual pole. So that's pretty much it. This is the model that they want you to not know, right? That these two things are working together to create your globe Earth. There is no other way around it. They have always done this. They need the layer of obscurity provided by two separate spherical or ellipsoid models in order to put this over, right? So you get this working together. And again, they show you the opposite, right? They say, hey, we have our Earth, and which is why we necessitated the need for our two models here to properly quantify, navigate, and, you know, et cetera. And again, in reality, it's these two equal this. And then, of course, when we go through all of that, it's these are creating this in the first place. And that's pretty much it. That's what I got for gravimetry and the study and the gravimeters. Local only.
Fantastic
so
Prezi.
much. Once again, so much for mass attracting mass, boys. I disappoint.
Yeah, all they know is that things fall at a little slightly different rate wherever you are on Earth. It doesn't matter where. It only matters that it varies by this amount.
Yeah, and then with the
Well, it
freedom
was,
to map it on their model of choosing, they just wrap it on their favorite ellipsoid, and they're good to go. And then it looks like that. It looks very undulation-y and, you know, gravitational potential changing, but it doesn't actually mean anything really. And as Stone pointed out, the scale of it is so insignificant that it's not like it, you would never know. So like adding this model to it isn't a way to say like, hey, we measured the shape of the Earth using these gravitational potentials. They're literally wrapping it around the starting model that they started with, which is derived from positions of the stars, taking zenith measurements.
Yep, can't have anything. Can't have this without this. So I guess the question then is, can you independently have a geoid model, or can a geoid model independently tell you about the surface of Earth? No,
And
absolutely not.
That's a strong point that India was making. You know, you need that reference ellipsoid. The reference ellipsoid is the backbone of all of it.
Yep. So everyone should learn about datums and reference ellipsoids because that is the globe. And when it comes down to it, most people in the average everyday lives, most people you argue with, certainly globers on the internet, none of them can differentiate what is in fact an abstract spherical coordinate system from the supposed globe Earth model. Like not one of them could adequately differentiate this from this. Which is how we get everyone thinking that this is real and we all live on it.
So they just use our own taxpayer money to hoodwink us. Nice.
To pay people to do the things that then they lie to us about. Yeah, exactly.
Thus, the cycle is complete. Very cool.
Any other questions, contributions?
The same trick they did with the graticule and the datums.
Yeah. Yep. So you have the celestial sphere and the terrestrial sphere. That's one model put forth by Ptolemy so that you can understand and map the world. That's the basis of cosmography and mapping. And then when they do their modeling for, say, WGS84 and all the constant stuff, they need one more model. We'll just combine these other two models that are totally real, and we'll use them to create this construct Earth. So really, it's like the globe Earth is an amalgamation of all three of these models. All you got to do is add a geoid to this animation, and I think we'll get the whole context, is that it's only ever created by this.
Did you find any mathematical relationships between the variance in milligauss to the deflection of the vertical relative to the latitude that they said that it was measured at? Is there
No,
any justification for my plumb bob being, you know, XYZ arc seconds off due to the actual measured 9.8 meters per second squared deviation at that laddie? Is there any
no.
correlation?
Nope. And in fact, I found it very peculiar that I could
Dude.
find zero maps of this latitude dependency. Like, I want to see a gravitational map with bands that go from the pole to the equator, because that's exactly what's supposed to happen on the globe with a latitude dependent variation in G. The fact that they forego and ignore all of that to do these complicated interferometric, you know, specific measurements of who gives a shit, instead of showing me the latitude dependent G, that would be a nice map. Like, I don't understand. And I guess the reason that the plumb bob gets pulled, Alan, varies by year or month or whatever. So I don't know how you justify that being a mountain. Like, you know what?
Yeah,
This mountain's extra pulley this month.
So that would like imply that your deflection of the vertical would have to justifiably change month to month then. Right? You couldn't have a consistent deflection of the vertical due to gravitational potentials if the fluctuations are random and offset. I mean, randomized and not constant. You would never be able
Yeah.
to justify your original offset.
Yep, but they keep making new models, and then all their offsets are relevant to that new model. So I don't know if it's every year, but every time they make a new model, all the subsequent references are to that new publication or whatever. So
in
it just
this
goes
in
on.
this sorry, in that particular the last slide, yeah, this one, do you notice it's like kind of going kind of circular? Like Alan was saying, it could be related to the seasons, you know, the movement of the sun during the year.
Seems like
Yeah, I would
everything is
almost.
related to that. Yeah.
Yeah, I was gonna say it's a pretty good bet that whatever we're seeing is a direct or indirect result of the dynamic cause and motion of the sun and the moon, as almost every dynamic system on this place seems to be.
It does
So.
look kind of circularish or something. You notice that there's a symmetry.
I mean, so if our, you know, electric sun and magnetic moon kind of work together to create electromagnetic energy as they move and interact throughout the time, and they traverse, say, magnetic lines and magnetic fluxes through a toroidal vortex pattern, which explains the motion, then what we could see here, yeah, we would expect to see, hey, variations dependent on their proximity and where they are at any given time, and that would affect, you know, the variation on the, let's say, the downward force of the magnetic vector that it creates. That would be my hypothesis.
It would be interesting to compare this to a tides map, like a monthly tides map, and see if they correlate.
Yeah.
Shane, do it. Do the thing.
Okay.
Do it on the fly.
We could definitely do that.
My plumb bob and your plumb bob sitting on the geoid. My plumb bob and your plumb bob.
Went backwards again. All right. Presenter mode. Share. I went backwards again.
Fast enough, Shane.
Dude, it went. Maybe I got to do it when it's over here. Share.
You have to outclick
present.
the processor.
Like, I want to present and then have you do that. Okay, perfect. Yeah, it's just gotta. Whatever you want, back it up. So, of the tides presentation, we got to go all the way to the end. There's many, because we were looking at my immediate thought was to compare it with infodromic points, or maybe even the tidal constituents map. Maybe let's start with tidal constituents. Something like this.
You could also throw it on the one that you did for meteors, the meteor showers.
Yeah, the sporadic toroidal Hellion, anti-Hellion vortex points, and maybe
That's one of my favorites.
In a different coordinate system, though. It's tough to overlay that.
I just do it anyway.
Well, this is as hours go by, but the original the A map we were looking at was as months go by.
Yep,
Yeah.
That's a good point. Let's see here. What's this one? I'm not even sure of the time frame on the scale on this one, but this is So you can actually see the infodromic points, the points of zero tidal implication, tidal amplitude over here, the points at which the tide doesn't actually go up and down, but around which they appear to have massive fluctuations. That's what the infodromic points are. This one too, you can kind of see them. There's one over here, And you can see that the high oscillates around with the low and around this point right here for whatever reason that is. A couple more maps over here at the end. Oh yeah, tidal constituents, tidal amplitude, those are the winds. Telluric currents. There we go. M2. Yeah, I bet that magnetic anomaly we were just looking at actually looks a lot like this. That's definitely by the day. I wonder if I have any tidal
It's by every 30
animations
minutes.
by the month. Yeah. I'll have to do an overlay of the milligals on a specific and relative comparative time frame with anything to do with the tides.
Hey Shane,
So,
those devices, it's like look like a vertical interferometer, right? That how they measure these things, right?
yep.
How did they get the free air version? Do you know?
Free air version. I thought a lot of them are using vacuums.
Well, no, I mean, like how do they measure? Did you happen to see how they actually measured like above ground? Like they use planes with those interferometers? Because my question is, to me, it seems like the hot spots of where these occur, the either the low gravity or high gravity, is like maybe major cities is where they would actually run the tests, and maybe on a 1 day calibration is off, so it measures low, and next day they measure it again and it's a little higher. So I'm wondering if it's correlates to whatever city they're in, and that's where the hotspots are actually occurring, wherever these devices are and wherever they're measuring these things. Because I wouldn't think they can measure the whole planet. I mean, I would think they would just do it in certain cities and then just kind of do a guesstimate of, this city measured this much at this university, so all around it, it would be a hotspot of either low gravitation or high gravitation. That's my thought about it. That's why it looks off at certain seasons. And anyway, that's what I would guess is why it looks hot. More gravity in one location, less gravity. Like the India one looks like it's more blue at and like it would, I would think like there's a city in there that would have these devices compared to Africa or South America, and where there probably wouldn't be a university with one of these devices where they wouldn't measure as much. What do you think?
Yeah, I mean, so all of that would be a real question, and that would be like if they were actually measuring the real variance in G, like so the wide swing of 0.7 meters per second as you get from the North Pole to the equator. That would be interesting to map out. I think what you're talking about may affect something like that if they were to take real measurements, but instead they're playing make believe with a hundredth of a degree of milligals of a tiny variation to an adherence to a specific hypothetical perfect model of the ellipsoid. That's what the variation on G is. Remember when we started how insignificant that is and what they're doing. So what you're saying is almost as if they care what the measurement would be, and if they wanted to try and figure out what a dynamic cause would be, they might take action like you described, but I don't think that's the case.
No. No. This is kind of like complete guesstimation, and the only variance is where they do the measurements, and that's the only difference is places where there is no interferometer to make these measurements. They kind of just guess, and just throw it out there, and whatever measurements they do have, they have to kind of build a model around it. But it's all, in my opinion, it's all just guessing. And I mean, I don't see how they can even calibrate these devices all to measure the same exact thing anyway. It's just all guesswork, in my opinion. From an engineering background, it's like, how would they even calibrate it at a certain day or a certain month and take a measurement all around the world? Is just, I just can't see it happening.
Yeah, I mean, I don't understand why they think this is important either, which is why I put it in my first slide. Like, here's the reasons why they think they need to measure local g or little g with this degree of specificity, and I couldn't even read them because they're so retarded. Determination of the geoid, which is the only one principle, right? We need it for our model. That's what this means. We need it for our model. We need to do it for our model. We need it for it hides other layers of our model. Don't ask questions. Don't worry. This I saw was a throwaway answer. Tectonics, and you need to measure local G for what? You're predicting earthquakes and post glacial rebound, PNS waves for local flat Earth seismology, maybe. Influence of atmospheric cryosphere and hydrosphere on Earth. Yeah, I mean, so the tiny milligal variance of plus or minus 80 milligals is going to influence Earth's atmosphere. Okay, structure of Earth's interior. Yes, only because they're making wild, subjective, interpretive guesses on the mass attracting mass dynamic framework, meaning that thus there must be a density gradient or a gap, let's say a cavern directly below where we measure our gravity anomaly. That's what they're presupposing. Nothing that they're doing actually backs this up or has any substantive proof or even leans evidence towards that direction, to be honest. And then they say, this is the one that Tony said for geology and mineral resource exploration. So he says that they find minerals by finding the dense spots using gravimeters. That's what they say this is for in the study of geophysics. So how that's going to help them to detect minerals better when they eliminate the actual band in which the fluctuation happens, right? Latitude dependency, zero at the equator, higher at the poles. We like what they say is we know it varies by a lot, but we're going to ignore and minimize all of that so that we can focus on this other variation, which is just going to be dependent on our presupposition of a model. We're going to assume a perfect ellipsoid, and we're going to measure our deviation from that. Like, how is that helpful in any sense for engineering or for anything? Like, I don't understand. But that's what they say. That's what the textbooks say. That's where all the study of geodesy lies. That's where these complicated diagrams call. I know for sure things like GNSS and WGS84 and Google Maps and satellites and GPS all work exceptionally fine and will get you anywhere you're going with your adherence to your internally consistent WGS84 ellipsoid model.
Did you notice in your notes, like from the mainstream, did you notice that they got Newton and they had Einstein in there, but they also slipped in Cavendish at one point? Did you guys see that?
Yeah, because I was trying to get it to justify little g being a mass attracting mass, and it was like, well, we know, even though it was unrelated, it was like Cavendish. Forget, yeah. But again, so this is computed as the irregular equipotential surface showing where real gravity and topography deviate from the smooth ellipsoid. That is what this is. That is all this is. Again, ignoring the wide variation by latitude and all the other real world effects that we know of. We're going to ignore all that and we're going to focus on this tiny 0.00005 meters per second square variant. That's what this whole model is for. So it's either that or it's really just like as the interpretation for LIGO is a iterative neural network layer or another sort of obfuscation layer through which they can hide and obfuscate real world data and measurements and observations into presupposed spherical ellipsoidal models.
So let's say that this worked, right? Like, wouldn't they be able to show pockets of high gravity, and wouldn't that show like maybe some heavy metals such as gold? Wouldn't this make someone rich? Is that what they were talking about? Mineral, like locating different minerals? Like this could be like really could make someone some good money if it actually worked, you know? I haven't seen anything like that.
It can't even justify their local deflection of the vertical on the ground. So, like hypothetically, if it did work that way, then like, yeah, they could use it to identify minerals and whatnot and density pockets of nice loot that they're looking for. But none of that seems to be the case. And even in terms of GPS, where they would make, general relativity gravitational potential corrections for these types of things, like if they go as far as to say that on the ground, my plumb bob is, being deflected, it's not going toward to the center. there should be wavelength changes in light at these different potentials, and they say that because the ellipsoid is spinning through its own gravitational field, that creates an equipotential offset, so they can just treat it as a uniform gradient. So even with these milligauss measurements from an interferometer on the ground or whatever, they don't even use it to correct any potential gravitational potential differences per latitude for GPS, which would be absolutely mandatory if this was real.
Funny. That's so funny that they ignore all the biggest, like, why, like, all the things you actually would need to account for and would be interesting. They're like, nah, nope, don't care. Doesn't matter. Eliminate. That's so funny. Dual pole. That's
Like,
yeah.
they're like, how come you guys don't correct for this? Like, well, what's happening is the uneven parts of the gravitational field are being rotated through from the uneven ellipsoid, and it's creating a perfect offset that makes it an equipotential gradient all the way down. Sweet, dude. That's badass.
Except we know that it's, you know, this different for the free air gravity anomaly, and we know that it varies when you get to the local level, and we know that that's different from the surface level. So we know that it varies all the way down, but it's suspiciously constant for the formula.
Suspiciously constant. Yeah, they give a lot of contradictory explanations, and then when they try to present measurements like this small as if they're making some sort of substantial correction to anything or give an explanation to anything, it doesn't even explain the other corrections that they do, or it directly contradicts it because they'll turn around and say that it's just a homogeneous gradient anyway.
Yep. Super contradictory. Like we need to account for it in here and on the surface, but not in space where we're super sensitive and wailing through that same field. That though doesn't matter up there, definitely matters down here. Pulls my plumb bob, ignores my satellite.
Pulls on my physical
otherwise, that's
object,
it.
ignores the light. It's awesome. All right, yeah, dude, that was a great Prezi. Thanks for breaking that down, taking it back to the source of overlaying the measurements to a already conceived model to get the result that they want, to try and justify the other, try to justify it as a single cohesive model.
Yeah, it's all incredibly circular. Like, this exists. We know this exists because of this, and we know this exists because of this, and this exists because of these two. Like, duh. Obviously, you know what it reminds me of is how Eratosthenes
The globe
proved
trinity.
Aristotle
Dude,
proved,
it's,
yeah.
it's the globe trinity, dude. The geoid, the ellipsoid, and Mother Earth, or whatever. Or Mother Globe. I don't know. We can figure it out. But yeah, there's a circular structure there.
You know what I find really confusing is that if you ask a globie that, okay, if a helicopter is hovering above Earth, how come the Earth doesn't rotate, spin below the helicopter? And then they'll say, oh, because the atmosphere is spinning with it and it takes the helicopter along with it. So it looks like the helicopter is just hovering over one spot of a Earth that's not moving, right? But then the clouds are all fluid. They're just moving around like they want to. And then even the water in the ocean, you would think if gravity is pulling at it so hard that it's keeping it like basically curved along with the earth, but then it's still totally fluid. I don't get it. Like, you would think those things, water would not be quite as fluid. Maybe clouds wouldn't be moving as freely. It just doesn't make sense. Like, where's gravity for those clouds and the ocean water?
I just wanted to click on my own reference to see if it provided any information as to why this is so goofy and changes all the time, but it doesn't. You guys can go check it out if you want. That's where I got it.
All right, lads and ladettes, we will wrap up for the night. Thank you, everyone, for coming out. Shane, thank you for the awesome Prezi. We will be back on Friday for the Twitter community space. See what the lads are doing on Twitter. Then we'll be back. Then we'll be back on Glowbusters for Sunday to do another rendition of the gravimetrometer.
It'll
You
be
did that on
Charlie's
purpose.
birthday.
I did. I couldn't help myself, dude. Have you ever, dude?
Birthday on Friday.
It will be that her birthday on Friday, and we'll be having a little pre-celebration on Discord. So hang out on Friday for that. But yeah, Shane, you know the scene from Big Daddy where he's trying to teach that dude how to say hippopotamus, and he's like hip hop eponymous. That's how I read gravitometer. I'm like, gravitometer hippopotamus. All right, we'll see you guys on Friday. Later.